Hey everyone, today we're going to talk about the system of complex numbers. The goal of this video is to correctly define what a complex number is, realize that we have a brand new system of numbers, and with this system know that we can perform operations like addition and multiplication, but we just have to be careful about what those definitions mean in this context. The motivation behind a complex number comes from the idea of taking a square root of a negative real number. We've probably heard someone say before that you can't take the square root of a negative real number. This is kind of half true. The better thing to say is that you can't take the square root of a real number and then get a real number back in return. Taking the square root of a negative number is something that comes up commonly in the field of math, so the question is, what do we do about this? How do we handle taking the square root of a negative number? We'll start off with this definition. Let I equal to the square root of negative 1, which also means that I squared comes out to be negative 1. There are many results that support why such a definition exists in the first place, but none of these results are necessarily needed for a college algebra class, so we can take this definition on faith at the moment. This number I is called an imaginary number, and this is what is going to give rise to our system of complex numbers. So now that we know what I is, we can define a complex number. A complex number is one that has the form a plus bi, where a and b are both real numbers. And of course I, which is defined to be the square root of negative 1. Really, at the end of the day, you can think of a complex number as one that comes from real numbers. A and b are real numbers, but you have I, which is pretty distinct because even though it does come from a real number, it is itself not a real number. Another way to think of a complex number is just this new kind of number that has more moving parts, so to speak, than a real number. Namely, we have two moving parts. We have this component a that doesn't have an I attached to it, so we call a the real part of this complex number. And then we have b. The b is attached to an imaginary number, so we call b the imaginary part of a complex number. This might be a little weird to think about at first, but when you do see a complex number written as a plus bi, we're only talking about one number in particular. Even though it is expressed as a sum, this is still one number. So this is the simplified version of what a single complex number looks like. You can't simplify further because b has an I attached to it and a does not. So this is as far as we go. And any time that someone is referring to a complex number always has a real part and an imaginary part. So make sure that you're comfortable with these definitions. By standard convention, when writing a complex number on paper, you write the real part on the left and the imaginary part on the right. We'll go through a few examples and name each part of these complex numbers. Take 2 plus 7i. This is a single complex number whose real part is 2 and imaginary part is 7. Earlier when I said that a single complex number has two moving parts, this is what I mean. When I look at 2 plus 7i, that is a single and unique complex number that has two distinct parts to it. The fact that we have two unique parts here is what sets apart a complex number from a real number. That and the fact that there is an imaginary number installed into this. For the complex number minus 3 minus I, we get a real part of negative 3 and an imaginary part of minus 1. Like always, we have to pay close attention to signs. If we just have the complex number I, it has a real part of 0 and an imaginary part of 1. In general, if all you see is an imaginary component to a complex number, the real part is going to be 0. When we look at 4 as a complex number, the real part is 4 and the imaginary part is 0. Lastly, the complex number 7i minus 3 has real part negative 3 and imaginary part positive 7, and we can flip the order of this number so that it's written in standard form. That comes out to be negative 3 plus 7i. So now that we understand complex number anatomy, we can go ahead and start talking about what it means to add and subtract complex numbers from one another. It's pretty straightforward because essentially all we're doing is combining like terms. And we're always doing this with respect to the imaginary number I. In general, say that I'm adding a plus bi to c plus di. So this is just the sum of any two complex numbers. After combining like terms, I see that I add the real parts together, and then I add the imaginary parts together. We see also that we play the same game with subtraction. So I'll subtract the real parts from one another and the imaginary parts from one another. As always, we'll go through some examples. Say I want to compute the sum of the complex numbers 3 plus 7i with minus 2 plus I. Combining like terms gives me an answer of 1 plus 8I. The real part of the sum came from 3 plus negative 2, and the imaginary part came from 7 plus 1. In the next example, take 2 minus 12I minus 4 plus 2I. We end up getting an answer of minus 10 minus 14I. The last thing we'll talk about is how to multiply complex numbers with one another. We'll start off doing simple cases. Consider the multiplication of 2 with the complex number 1 plus I. All we have to do here is invoke the distributive property. So we'll distribute the 2 across the sum and get an answer of 2 plus 2I. Now consider I times the complex number 2 plus 3I. Same kind of game, we'll go ahead and distribute the I across the sum, and then we'll start simplifying. The only difference is an I squared term is showing up here. And all we have to do is remember that by definition, I squared is the same thing as negative 1. Once we substitute a negative 1 in for I squared, we simplify and get a final answer of minus 3 plus 2I. For our last example, consider 2I times the complex number 1 minus 2I. Same thing as we did above, we'll distribute, we'll simplify, we'll take care of the I squared term, replacing it by a negative 1, simplify further, and get a final answer of 4 plus 2I. This multiplication didn't invoke any new rules other than how to properly handle I. In the next slide, we're going to talk about a more general kind of multiplication with complex numbers. So let a plus bi and c plus di be any two complex numbers. To multiply these numbers, set it up like so. Since we're multiplying two quantities that each are their own individual sums, we will use the FOIL method to carry out this multiplication. The first terms are a and c, the outer terms are a and di, the inner terms are bi and c, and the last terms are bi and di. So this is exactly the FOIL method that you would see if you were multiplying two linear polynomials. We do have to take an extra step to simplify because we see an I squared term showing up. So replace the I squared term with negative 1, and then once you simplify, you get a final answer of the quantity AC minus BD plus the quantity AD plus BC times I. So when we multiply two complex numbers together, we get a complex number in return. Our final answer here has a real part and an imaginary part. Generally, this is not a formula that you have to memorize to do this operation. You just have to remember the FOIL method and to properly handle the I squared term that may appear. Let's run through some examples. We're going to multiply the complex numbers 1 plus I with 2 plus 3I. As we FOIL this out, we get 1 times 2 plus 1 times 3I plus I times 2 plus I times 3I. One round of simplification gives us 2 plus 3I plus 2I plus 3I squared. After combining like terms and replacing I squared with negative 1, we get a final answer of negative 1 plus 5I. For our next example, multiply minus 2 plus I with the complex number 3 minus 4I. As we FOIL, we get minus 6 plus 8I plus 3I minus 4I squared, and then we simplify and take care of the I squared to get an answer of minus 2 plus 11I. Last example for the day, we will multiply 3 minus I with 3 plus I. First we FOIL to get 3 plus 3I minus I squared, which simplifies to 9 plus 1, giving us a final answer of 10.